Good afternoon, Professor Chow, Professor Bahnfleth, colleagues, students, ladies and gentlemen. Welcome to this pair seminar series. And today we are very happy to have lecturers from Penn State University. Professor Chow will introduce shortly. Pair conduct research seminars, lectures, workshops from time to time, and we'll like to invite all of you to the future seminars as well. So now I'd like to have Professor Chris Chow, Senior Vice President for Research and Innovation, to introduce our speaker today. Professor Chow, please.
Ladies and gentlemen, it is my great pleasure to introduce our seminar speaker today, Professor William Bahnfleth, Professor of Architectural Engineering at the Penn State University, USA. Professor Bahnfleth's research interests mainly focus on the control of indoor environmental quality and its impact on the energy use of buildings and the utility systems that serve them. As a registered professional engineer, Professor Bahnfleth actively contributes to the field in different capacities within professional and representative bodies. He served as the president of the American Society of Heating, Refrigerating, and Air Conditioning Engineers, SJ, during 2013 to 14. Following in the footsteps of his father, Don Bahnfleth, who served as president of the society in 1985 to 86. Following his term as president, Professor Bahnfleth continues to serve as SJ in leadership positions. He led the society's initial response to the COVID-19 pandemic as the chair of the epidemic task force, steering the society to develop a national pathogen control standard at the request of the White House COVID-19 response team. Throughout the pandemic, he gave over 200 presentations and 150 interviews on this subject. Professor Bahnfleth is a key figure in the establishment of the Indoor Environmental Quality Global Alliance, IEQ, which brings together an interdisciplinary international working group of societies to address all aspects of indoor environmental quality, from indoor air quality, thermal comfort, lighting, to acoustic science. He has been widely recognized for his 30-year-long dedication to elevating indoor air sciences and serving humanity through teaching, research, and professional service. Professor Bahnfleth is the author or co-author of more than 180 peer-reviewed publications. Among the many awards bestowed on him, he received the F. Paul Anderson Award, SJ's highest honor for technical achievement. Without further ado, ladies and gentlemen, please join me in welcoming our seminar speaker today, Professor William Bahnfleth.
Well, thank you, Professor Chow, for that wonderful introduction. I hope I can live up to it with my talk. And I want to thank Professor Chen and Per for inviting me to speak on this seminar series today. I understand there's a big audience outside of this room, and I welcome them and hope that there's something in my talk that will be useful to them in the future. Like most academics, I've given many technical talks in my life about my research and various engineering subjects. And in the last few years, partly because of my experience during the pandemic, I've been giving more talks like the one I'm giving today, which relate more to the contexts of science and engineering and society and how we go about actually achieving the outcomes that we wish to have. I've now had a long career, as you've heard, in indoor environmental quality, and I feel that we have not made as much progress as we ought to based on all of the research that's been done, and I've been devoting a lot of thought to how we might do better in the future. So that's what my talk is about today, and I hope you'll find it useful. So before I go into that, I did want, for those who are interested in where I'm from, to show you a map and a couple of pictures. Penn State is not the University of Pennsylvania. When I say I'm at Penn State, people often ask me how I like living in Philadelphia, and I say I don't live there. I live in State College, which is a little town in the country. So we're about a 4-hour drive from Philadelphia and 2 hours from Pittsburgh, but also close to Washington, D.C. and Baltimore and New York. So it's a very nice place to live, with many big cities to visit. This is an aerial view of State College, and you can see the university here in the center. I'll point out for the golfers in Hong Kong that there are 2 public courses owned by the university where the greens fees are $23. And here's another one, and there are 2 or 3 more that are just off camera. So we have a very nice community and lifestyle there, and you can see that it quickly blends into farmland. I'm fortunate, after 30 years, to finally work in a new building. The Engineering Collaborative Research and Education building is the newest academic building on campus, and we've been in there for a year, and it's really going to help our department grow in the future. You see the blue arrow on the figure on the left. That's the view that you get in this last picture, looking down campus, and you can see some of the mountains that surround us. You can also see that about half of the area of our campus is athletic facilities, like many big universities in the U.S. And I'll specifically mention our football stadium there on the right. It has a seating capacity of about 107,000, making it the 4th largest stadium in the world. The 2 largest are Modi Stadium in India and the stadium in Pyongyang in North Korea. And the next 8 are all U.S. Football stadiums at universities, for whatever that's worth. But as you can see, it's a lovely place to be. My current research focus is based on 2 projects from the recently awarded ARPA-H BREATHE program. ARPA-H is a government agency, and they've recently funded a large program directed at achieving building resilient environments for air and total health. The vision is smart building systems that monitor and respond to changes in indoor air quality, and you can read about that program at the URL. There are 3 main tasks. This program, despite the rather general vision that's given, is focused on bioaerosols. So the first task area is to develop near real-time biosensors that can produce information that can be used directly in risk assessment and fed into building controls. The second task is to develop the risk assessment tool to use the biosensor data and also other information on indoor environmental quality that is collected. And then the third part is to test that system in a number of different test beds. It's a 5-year, $150 million program, and there were awards to 4 teams, and Penn State has participants in 3 of the 4, interestingly. So that's me. Let me say that I felt this would be an appropriate topic for this audience because I read what PEAR says about itself on its website, and I think the vision and mission here are very aligned with the goal that I have for this talk, especially the second bullet under mission, to create societal impact of the Institute's research. That's really what, as academics, I hope we are all striving for. So that is what I will be trying to help us make progress on today. So for indoor air quality, what are our aspirations? I tried to write down here at the end of my career what sort of things I think are important. I think we should have buildings that keep the occupants safe from the normal contaminant exposures that may occur in them, whether it's occupants or building related sources or outdoor sources. We should have buildings that are resilient with respect to indoor air quality. This is really a new thing. We didn't talk about it much, and certainly our standards didn't show it until the pandemic happened, and now we're very concerned about what we do when there is something like an epidemic or pandemic disease that is in circulation. And also, increasingly, and we think because of climate change, we're seeing a lot of extreme outdoor weather events that may affect air quality, specifically wildfires. At one time in the US, we thought that wildfires were simply something that happened in places like California and Washington and Oregon on the West Coast when the ground cover would burn off periodically. But now what we're seeing is almost every year significant forest fires in Canada, across Canada, that blow down into the entire US. So even in Pennsylvania, we're getting very bad air quality at times because of wildfire, and we need to think about how to design our buildings to deal with that. And then third, buildings that have indoor air quality that supports wellness. We've lived with the definition of health for a long time that simply meant preventing long-term disease incidents. If you look closely at what the definition of acceptable indoor air quality in those standards, it's keeping contaminants below the limits that have been set by authorities that are known to cause significantly increased risk of lifetime chronic disease. But health means more than that. It's really realizing our potential and being able to be resilient and improving our productivity and things of that sort. And finally, to the point of what my research focus has been for many years, having buildings that achieve these goals sustainably. So we're not compromising the outdoor environment or energy supplies or other things that go along with sustainability. So that's what we'd all like to do. And anyone who's been in this field for a long time can ask themselves how close we've gotten to achieving those over the last 20 or 30 years, despite what we have known from research. So here's an overview of some of the points that I want to talk about. The first is that I think there's an obvious gap between science and practice. Not that they don't understand one another, but that what's being done in the scientific community takes a long time to filter into practice in many cases. I think that this is a gap that can be closed, but only if we realize that science and technology are not the main barriers to progress. We've seen over and over that that's not the case. So I've listed a number of challenges here that I'd like to talk about briefly in the time that I have that provide the additional issues that we need to think about. Science and technology, certainly there are issues, but human behavior, our understanding and management of risk and uncertainty, standards and regulations, regulatory processes, and even political processes all play a part in actually changing the world around us. And the simple answer to this, which needs a lot of elaboration, is that success can be found through broader engagement and cooperation. Horizontal engagement amongst our academic peers, our scientific and technical peers, but also vertical engagement with other levels of society that are involved in getting things done. So we need vision, planning, and persistence that sometimes has not been in strong evidence. So as I've already noted, indoor air quality science has given us a lot of knowledge, but there are many gaps. If we look at the beginnings of what we might call modern indoor air quality science, they go all the way back to the mid-19th century, and you can go even farther back if you want to, but this is when the names that we start to hear as being the earliest proponents of better indoor air quality are named. There was a recent literature review based on studying Scopus database and papers that had indoor air quality or IAQ in them, and they found over a 5-year period 1,700 publications and as many as 330 in 1 year. I actually think that's low in terms of the total amount that's written about indoor air quality, but even 330 papers a year represents a large research effort. And another recent review noted that there's still a lack of comprehensive evaluation of peer-reviewed IAQ studies to help understand the progress and limitations of IAQ research worldwide. So we know that we could do better despite the mountain of research that accumulates. So what questions would we like to answer as scientists, as engineers, as researchers? First of all, what exposures are important? That's something we've been studying for a long time and still have not entirely reached consensus on. Particles, gases, bioaerosols, we know that all of those are important, but how much harm does each of them cause, and which ones specifically do we need to measure and control in the indoor environment? Secondly, what are the effects of these exposures on the microscopic and macroscopic levels? Chronic and acute diseases, healthcare costs, productivity. We need to relate the exposures to the effects, because then that leads into an economic analysis that helps justify doing something about it. And then finally, how can we control those exposures? Source control, the best way, dilution with outdoor air, but that brings energy penalties, mechanical filtration, and many kinds of air cleaners. So those are the things we'd like answers to. There's a nice database that tries to summarize existing knowledge that Lawrence Berkeley National Laboratory has put together, and you may find it interesting to browse that site if you have not done it before. Well, so how have we done? I'll just ask one simple question. After 200 years of studying it, shouldn't we know what outdoor airflow rates in a building should be to have acceptable indoor air quality? The figure here comes from a paper that was published in the ASHRAE Journal on the occasion of the 100th anniversary of ASHRAE, and you can see that from Treadgold in the early 19th century to Billings and Fluga in the early 20th century to mid-20th century to now, we've gone from 4 CFM per person, about 2 liters per second per person, to 30 CFM per person, back to 10 CFM per person. Based on Yaglu's research, Billings and Fluga were promoting 30 CFM per person because of concern about disease transmission. And Yaglu said odor is really the thing we need to worry about. And that remained the standard until we started seeing a lot of sick buildings in the 1970s and 80s. And now we're back to about 15 CFM per person, which is roughly where Ole Fanger and others at Technical University of Denmark pegged the ventilation rate that would result in 80% not dissatisfied, the perceived air quality standard that we also tend to try to maintain in buildings. So we really haven't made up our minds about exactly how much outdoor air we need or how much removal of contaminants. And history repeats itself. In the early 20th century, we had a big scare about bioterrorism in the United States, and that coincided really with a global concern about biosecurity. And after there were some terrorist attacks in the US with weaponized anthrax, there was a big effort to figure out what we could do to make buildings safer. And so I participated in the group that wrote this paper in 2006 on improving performance of HVAC systems to reduce exposure to aerosolized infectious agents in buildings. And then buildings did not change. Everyone perceived the risk was really very small to their building. They didn't make any changes. And then 2019, 2020 happened, and the world was taken over by SARS-CoV-2. And we wrote articles like, how can airborne transmission of COVID-19 indoors be minimized? And surprisingly, it gives the same list of recommendations that we gave in 2006. And we can only hope that now there is the recognition that this is important enough to do something about it. And then this happens in other ways as well. You know, a little closer to home, 2004, the original SARS epidemic, and Hugo Lee and others published that the original SARS virus was transmitted airborne. And I think that was generally accepted. But then again, 16 years later, when SARS-CoV-2 began to be a big problem, it became a very serious, long-running argument whether it was actually airborne, even though its predecessor had been airborne. So again, Hugo Lee was involved in that. But now I think we have, at least for the time being, resolved that issue. And again, just to point out that I'm not only concerned about infectious diseases, we've had lots of data, lots of publications about the effects of indoor air quality on other aspects of health and well-being, like the work of William Fisk and collaborators about 25 years ago. And again, that has not really resulted in a lot of change in my country. And in 2020, Joseph Allen and John McCumber at the Harvard School of Public Health published a book on healthy buildings that essentially makes the same economic arguments again and updates them. So these statements about the importance of IAQ keep being made, but without a huge amount of change in how we design buildings. And frankly, my father was aware of this 40 years ago when he was the president of ASHRAE. This is a statement he made in State of the Society address in 1986. Indoor air quality could be the most important health concern we'll face for the remainder of the 20th century. And I will only comment on that he was half right. It's probably the most important health concern we'll face for the first part of the 21st century as well. All right, so that's the case that we're not really doing what we would like to do to achieve the goals that we have. What are the problems and solutions in the scientific and technical arena? The problems: not identifying the most important questions. Sometimes researchers work on the things that they find interesting or that they can find funding for, and we don't necessarily identify the most important research priorities of society. Many questions are only answered partially because the solutions are only partially funded. That's not the researcher's problem, but when you have a hard time getting research to work on what you think is an important area, then you just have to stop and do something else because that's your job. And certainly I would say that it's true that science is usually not well coordinated with regulations and policy development in most countries, certainly not in my own. So how do we improve things? The first thing to do is to get out of our silos, scientific silos. We need to engage with other parts of society, and we also need translational research. I think this is a well-recognized issue, is that science does not turn itself into regulations and into engineering practice without some effort. And to make all of that happen, I think better support for major programs to solve these problems are needed. And that comes back to all of the various government and non-governmental agencies that will fund research and development. So a few words about technology. I don't want to suggest that we don't need any more new technology, but I think it's quite true that we have plenty of technology to do a lot better than we're doing. So I always try to disarm the argument that if only we had a new piece of technology that would do X, that would solve the problem. The problem is that we're really not using the things that we already have as well as we could. I think that one of the big hopes for indoor air quality sustainably is air cleaners, but we have a lot of gaps where those are concerned, and we didn't really start paying a lot of attention to them until we found out the things that we didn't know at the beginning of the COVID pandemic, and everyone wanted to use air cleaners. So what we got instead was a lot of weakly supported manufacturer claims. They would say things about how their technology worked, but if you probed, there really wasn't data to support it. So there's a need there for an evidence basis for how they work. And sensors, I think, are the technology of the moment. Everywhere I go, there is a lot of excitement about sensors and measuring things in buildings. And I think that it's true that the technology is becoming more affordable. We're getting more sensors for different kinds of contaminants, but I think there are some questions that we ought to ask ourselves before we start putting lots of sensors into buildings. If the first thing, of course, is what to measure. And if we're still not so certain about what constitutes the properties of good indoor air quality, then maybe we're getting out ahead of the game. There's a lot of interest expressed in continuously monitoring variables in buildings so that the owner will know at any moment in time what the formaldehyde concentration is or what the CO2 concentration is. Is that necessary? There are some purposes to which we could put that kind of data, but if we simply measure periodically and do recommissioning on buildings so that they're maintaining their as-designed quality, then maybe that's enough. And it's certainly an easier thing to do than instrumenting lots of existing buildings, many existing buildings. And then the final thing is, what do you do with the sensor data? So you've generated a stream of data for the CO2 concentration in every classroom in a school. What is the purpose for doing that besides putting it on a dashboard? I would say that one of the things that I would find the most useful, I think is the most promising, is knowing where people are in a building and how many there are, because that would support ventilation controls. But sensing that and determining it is not the same as controlling. And I find that many buildings really can't make good use of that information because they cannot turn down capacity on the granular level that you would need to do to actually make good use of it. So I know that the people are over in a couple of rooms on one end of a floor, but if I only have one system and it's either on or off, then what does that do for me in a practical way? All right, so those are the things that we often talk about in science and technology. Let's move on to maybe a little different subject, which is human behavior, and something that you will observe, I'm sure, many times during your lifetime, is that a good argument doesn't always win. You may have an airtight argument for a technology working, or indoor air quality being important, or the economics being on your side, let's say for energy, and still there is not investment in it. So we need to understand what makes people invest, and specifically how uncertainty affects that, and also the impact of how evidence is presented to try to drive investment. And that kind of information comes from a relatively new science, behavioral science. Daniel Kahneman and Richard Thaler are two of the creators of that field of behavioral economics, and I think they're worth reading if you've not ever seen any of their work. Poor choices are made all the time by people, as they've discovered, because they expect certainty, and also because in some cases uncertainty is not recognized when it exists. So here are a couple of thoughts on that, one from an old philosopher and one from a more recent one. Voltaire said that uncertainty is uncomfortable, but certainty is absurd. And that's something we have to realize if we're trying to change the world, is that we will never create the perfect 100% certain case that some say they want. And so we have to do a better job of presenting what uncertainty really means. Kahneman pointed out that blindness to uncertainty leads to bad decisions. Uncertainty has actually been turned into a weapon to prevent progress. Oreskes is a historian of science, and her book, written with Eric Conway, Merchants of Doubt, really relates to things that have gone on mostly in the US, but I think you would find it very interesting. And the whole thesis of the book is that it's been recognized by certain entities that if they can cast doubt on scientific knowledge, then they can stop things that they would not like to have happen from happening. So they're using the tools of science, the honesty of science, to say, we know this, but not to a certainty, to actually arrest development. And a partial list of the things that are covered in that book are listed on the slide. The dangers of smoking. So eventually it came out that companies that sold tobacco products knew decades before they admitted it that their products caused harm, and yet they were actively casting doubt on science that was being presented to regulate indoor smoking, or smoking at all, and delayed it, which certainly led to more illness and more death. Secondhand smoke was the next issue. So, well, yes, certainly, okay, we'll admit smoking is bad for the person who smokes, but the person who's in the room with them, that's okay. And we know that that's not true either. Acid rain, ozone depletion, climate change, all of these things have been treated that way. And although COVID hadn't happened when this book was written, I think they might have written something about the airborne transmission debate as well. And one of the key issues about COVID being airborne or not airborne is that if it's not airborne, it's an individual problem. You're not wearing your mask, you're not washing your hands, you're not social distancing. If it is airborne, then that becomes a problem for the owner and operator of a building. Is the building safe or not? So we had this debate. In March of 2020, the World Health Organization, for reasons that we may not ever fully understand, was still saying that COVID-19 is not airborne. And in fact, this tweet is still online today, as I understand it. At about the same time, this was when aerosol scientists and other scientists and engineers started to speak up that really the science suggested otherwise. So Lydia Morawska, who's been very prominent in this area, and others started to write papers like the one you see here. We should admit that that SARS-CoV-2 is airborne and take action against it. So this debate went on for a long time. I've shown the cumulative deaths that were being reported at that time. And back in March 2020, when this argument really got going, we were probably under 100,000 deaths worldwide. And by the time the World Health Organization and the US CDC made clearer statements about the risk of airborne transmission, it was 2021, and we were already between 3 and 4 million deaths worldwide. This is the consequence of delay. Just for your further reading, if you're interested in the subject, there was a nice academic paper written by a lot of people who were involved in Lydia Morawska's group on why there was so much resistance to the idea of airborne transmission of SARS-CoV-2 during the pandemic. And a very recently published book, Airborne, by Carl Zimmer, is a really nice historical read about the history of theories of disease transmission from miasma to droplet to back to airborne. What we've learned from all of this as far as how we approach indoor air quality in general and things like infectious diseases in particular is that the precautionary principle must prevail. I did not ever hear of the precautionary principle until I was in the middle of trying to lead COVID response, because it's a term that's used mostly in public health and in medicine. And a statement of that is shown here, that we should take reasonable measures to prevent threats that are serious and plausible. So if there's the possibility of serious harm and we can do something reasonable to mitigate that harm, then we should do it. And that was an approach that sadly aerosol scientists and engineers were promoting, and not public health authorities, at least not early in the pandemic in many parts of the world. The ASHRAE response in April 2020 was essentially a restatement of the precautionary principle that the transmission of SARS-CoV-2 is sufficiently likely through the air that we should take measures to control it. So we understood that, and RIVA in Europe and others in the engineering community made statements to that effect. So let's move on from doubt to this issue of behavioral science and people's willingness to invest. And it all comes down to whether a loss or a gain is in play. And some of you may go to casinos to make sure that you don't have too much money in the bank. When you gamble, it's a lot easier to bet if you're playing with somebody else's money, if it's house money as opposed to your money. So you put some of your money up and you make some, and then I say, oh, well, this is just money that I got that I'm not really at risk, so I can bet that, and pretty soon you're back to zero or worse. So Kahneman studied this scientifically and found that on average, people are about twice as willing to invest to avoid harm as they are to receive an equivalent benefit. So you're likely to spend more money if I tell you that if you don't, you're going to be hurt, or you are being hurt, as you would if I said, if you spent this much money, the things would be better than they are now. And so That's a principle that's been tested in a number of ways. With workers, they tried giving the bonuses to the workers at the beginning of the year. So instead of waiting to the end of the year to see if you'd done well and then rewarding you for it, they said, we believe you're going to do well. We're going to give you your bonus now, but if you don't perform up to these standards, then you have to give it back at the end of the year. And the performance of the workers was better when they had what they saw as their money at risk. And similarly, an experiment with wellness programs, opt-in and opt-out, there was more participation when it was opting out. You were giving away a benefit, losing a benefit, than if you were paying to get one. So this suggests that we really need to think about whether we should be promoting the concern about losses rather than the gains to be had. And now to Kahneman's point about unrecognized uncertainty. Just one example, I've spent some time working with Runa Anderson at DTU about occupant effects in buildings, and this figure on the right shows some data from a large number of identical homes and housing development in the Copenhagen area. So this is their annual energy consumption, and you can see that it is all over the map, from very low values to very high values. There is a mean in there, but what we learn from studies like this is that the occupants have more impact on the energy use of the building than the building itself. So that is something that we ought to be considering, is the factor of how occupants interact with their environment. In the indoor air quality arena, it's opening windows and running ventilation and all of the other things that we need to do. So now on to standards and regulations. I've spent a lot of time in this area recently because I've been chairing the development of the standard that was mentioned earlier, ASHRAE 241, control of infectious aerosols, but I've been teaching standards for design for a long time. Standards are the things that dictate how most buildings are designed, because they go into regulations that are enforced by building officials. And it's clear that most owners will not do more than they're required to do by the code. Certainly there are high value types of properties, Class A office buildings, et cetera, where it's become a commercial value to have higher air quality in buildings, but most buildings don't fall into that category. In order to write a standard, you need to have a consensus amongst all the concerned parties. That's good because then you have confidence that it'll be accepted. It takes that to be adopted in regulations. But the downside of it is that it tends to restrain innovation because everyone is pulling for their own personal interest in the standards process. We don't ask the people who participate in writing standards have no biases, because everyone has them. They simply have to disclose them, and then the committee is balanced to deal with that. The production of a standard is a long process. It can take 3, 5, 7 years, depending on the standard. 241 that I developed with the urging of the White House was really a different story. We did it in 4 months, but we had to cut quite a few corners to get there. But the point is that this is an arduous process. It can be frustrating for someone who's an activist because they want to see the world change right now. But my experience has been is that the folks with the most extreme goals tend to be the least likely to actually join the committee, where they can express them and where they can help working on getting those adopted into the standards. So I think that we need to have engagement in that process by more scientists and really by more advocates for better indoor air quality. The other thing to say about standards and regulations is that, at least in the United States, they don't govern operation at all. Buildings are designed to deliver a certain level of air quality, and after that, whatever happens is the owner's discretion. There's no requirement to report or to maintain. And this is really going to be a heavy lift to get that kind of regulation. So now to regulatory and political processes. I've come to believe over the course of my career that the regulation is critical, that we need to set requirements for how buildings are designed and operated, because voluntary programs, although they help raise awareness and there are some adopters, really don't work well overall. They change a small percentage of the building stock. It's mostly new buildings, not so much effect on the existing buildings. Regulations are effective even if we only raise them little by little in terms of their stringency, because they affect all buildings. And especially if we would institute operational requirements, that would affect many more buildings than are affected by our standards for the design and construction of new buildings. Regulation, I would say unfortunately, but for better or worse, is a political process, because eventually we're talking about city laws or state laws or federal laws. My observation is that we don't have success in the political arena unless we have public support for it. So now we not only need regulators involved in this discussion and those who understand science and technology, but we also need public support to encourage things to move forward. And you can think, I'm sure, of many political issues where that has been the case. And now you're subject to all of the vagaries of the political scene when this happens. So you have an election that turns the legislature or the executive in a certain direction, and now you say, well, we're going to have to wait another 4 years or 6 years to get this going again, because we're not going to be listened to in the short term. There are ways to deal with that, looking at other levels of regulation, but that is a problem. And researchers and practitioners don't participate as much as they should. One thing that I really give credit to my main professional society, ASHRAE, for doing is for having a strong government activities function, but not just at the society level, but also what we call the grassroots. So we have over 200 chapters around the world, and all of them have government affairs chairs in them, because as the saying goes, all politics are local. You have to engage with the local authorities using the system that you have. All right, so to make this an engineering presentation again, I give you a complicated diagram here at the end. I've put this together to try to give some sense of how all these things we've been talking about connect to one another. And the dashed box there in the center, we have research and technology, which contribute to standards, and then that is what goes into policy and regulations. But where does the research and technology come from? From recognized needs, and those can be identified by anyone, but it's essential that we feed those into this process. Research, technology, standards, we need a lot of outreach and education around them so that the public will be aware of what they should be concerned about, and then that will support advocacy, which is an important part of achieving policy and regulations that we seek. So this is my first try at it. I'd be happy to get ideas about how to improve this, but this is kind of how I see it. And you can find where you work most of the time on this figure and just think about how you can engage with other areas of it. All right, so I gave a talk in Singapore, I guess it was last week, on the way here, and it was on a somewhat similar subject, and I got fancy and titled it with a Latin phrase that I like very much, per aspera ad astra, which translates to through difficulties to the stars. And my point there was that if we want to be excellent in life, we need to overcome a lot of challenges. We need to be persistent, we need to be resilient, and we need to have the ambition to succeed. And I think this applies to all of the things I've been talking about, and I would encourage everyone to see yourself as someone who can be a real agent for change wherever you are in professional life or in your community, and to work for the things that you believe in. We can achieve success, even though it seems unattainable from where we are, if we recognize that that's only a starting point and lay out a path to where we're going and persevere in following it, even though there are going to be obstacles and disappointments along the way. And with that, I'll conclude and thank you for listening and look forward to the discussion.
Yes, well, thank you, Bill, for a wonderful talk. Now is our Q&A period. You know, for the audience inside of this room, you have a microphone just in front of you. You push the button and then you can talk. So yes, please.
Thank you for the fantastic talk. My name is Huifeng Du. I'm an assistant professor in mechanical engineering here. I'm glad you mentioned RH Breeze because I used to be part of a cohort to pitch to RH Breeze as well. And we were shortlisted, but we didn't make it in the end. You guys are probably just outperforming us, and congratulations on that. Yes, it's fantastic. And it's just like I have a little question about your opinion of the scope of the RH Breeze program. I had some reservation about the program from the very beginning, as the program asked for about 100 pathogens to be identified. That's a little bit like a moonshot to me, although they're always saying like RH, H for heart, but wouldn't it be more reasonable like to just pick a few like a representative pathogens at first and then trying to build the evidence and then like seek like general adoption of the technology before like going into 100 or 200 pathogens? And what's your opinion on that? Yeah.
Sure. Well, absolutely. It's aiming very high. Some have said that, you know, if you don't aim high, you're just going to be lower and lower in where you wind up. Yeah, I think some of the things that it aspires to will be difficult to attain. But if we get anywhere near them, then that will be big progress. I think initially the first gate is not 100 bioaerosol. It's a smaller number, 5, 10.
Yeah.
I think that's one thing, and that technology is coming along. How do you come up with a risk metric for overall IAQ that makes good use of information about allergens or infectious aerosols that are present in real time? Nobody's done that before. That's going to be difficult. And then we're supposed to show a very significant reduction in infectious disease incidence after implementing in the test bed. So all of those things are going to be tough, but I think we've got teams that are really committed, and we'll produce something of value out of it. Whether it'll be exactly what we aspire to and the vision of the program or not, I don't know.
Yeah. So in your opinion, what is particularly challenging about indoor air quality? Because like wastewater management and the outdoor air quality, we have a relatively like, I would say like accepted way of monitoring it. But what is special about the indoor air quality?
Well, it's much harder to regulate, you know, and it's different in every building. You know, if you're getting all of your water for the city from one source, you know what's in it, and you treat it, and you send it out. But the bad things happen to the outdoor air after it arrives in your building, and the occupants contribute to contaminant levels, and building materials contribute. So, and there are many, many more. You know, when we look at things like the outdoor air quality standards that the US EPA has, it's a really short list of things that are present everywhere, and we can establish limits, but there are literally hundreds, thousands of chemicals that may occur indoors and particles that could cause harm. Which ones do we measure, and to what levels do we control? And also, I think there's this issue of disaggregating the health and productivity effects of indoor air exposures from other factors that may also impact them.
All right. Thank you. Thank you very much.
Okay. Yes, please.
Hi, I'm from Clean Air Network, so it's a local-based NGO that do the outreach, advocacy, education track of your diagram. And I don't have a specific question, but I think there are a lot of science out there, as you mentioned, over 30 years. But in Hong Kong, I think since 20 years back, we have the IAQ management group established by the government, multiple departments. But since then, there's not much progress on the regulation side. We still rely on the volunteer regime to incentivize, provide some sort of public recognition for buildings to do IQ management. But then what we see, especially after COVID, there's not been much progress. There are a lot of various volunteer program, but then we think that the regulation could be the next battle. But as mentioned, is political. And then also coming back to my perhaps a question about what kind of occupants or buildings that you think we should prioritize to do more? Is that the vulnerable groups who stay long time in buildings, say students, youth, elderly, or who else? Yeah, thank you.
Yeah, that's a really interesting question because how you answer it may depend on what you see as the value. I would say right now in much of the world, parents care greatly about the quality of the educational environments. So from that point of view, schools are a good target because there's great interest in it. But on the other hand, schools are one of the less well-funded types of buildings. So it may be difficult to do much in some of those. The other type of facility that I would say that's becoming increasingly important is elder care. If you look at deaths that occurred during the early days of the COVID pandemic, the nursing homes and other similar facilities were really hit very hard, and many of those are not very high quality environments. The other would be healthcare facilities, of course. Something that we've learned from the COVID pandemic is that we don't know where the infected people in a hospital are going to be. So if you look at ASHRAE's healthcare ventilation standard 170, it has really only a handful of space types that are really designed to control infection. So airborne isolation, infection isolation rooms, operating theaters, some patient rooms, but a lot of other spaces are ventilated no differently than spaces in a typical commercial building. So I think there's scope there. And one of the things about healthcare is that you can quantify the impacts of interventions better. So if you're looking for an environment that will lead to data that will help move us forward, that's a good one from that point of view. So as you see, there are a lot of different approaches. And I was going to say to your comment earlier, in some places, what we would call a split incentive is a real big barrier to doing anything about IAQ. It's the who benefits and who pays question. And so if it's a public building, the benefits are the occupants, and it's the owner who needs to pay. And so do we put an unfunded mandate on owners to do something about their buildings, or do we take that as an advocacy issue and think about whether we should be trying to have it recognized that this is really a big national public health issue and that it's the kind of thing that should justify government incentives for changing the way buildings are designed and operated.
Thank you. Thank you for giving us a very important highlight and summary of what's the latest on indoor air quality. To follow your historic events, when Hong Kong experienced its SARS back in 2003, I counted the days. We experienced 10 weeks of disastrous environment. Before, probably 2 to 3 months before I stepped on the position of President of the Hong Kong Institutional Engineers. You also mentioned Yogo Lee. Yogo was the expert I tried to seek to help after I've set up a team, including officials from government, to look after the medical environment of the Princess Wales Hospital, because that's where SARS was discovered then. My question to you, sir, would be, if we were to define the regime we need to take careful air quality control, would you consider the medical environment be the first? Because that's the easiest, because we have the hospital authority in Hong Kong to do all the things, and obviously they will be able to deploy whatever sort of we call operation control that's necessary. And the other location that I suggest would be for location where there will be a lot of people assembled, like conventional halls, like schools, lecture rooms, and so on. And also, in particular, in the public transportation systems in Hong Kong. I'd like to hear your view, sir.
Yeah, thank you. That's a very strong argument. Certainly, we need to do something about healthcare facilities, no matter what we do about others, because as you say, that's where cases are going to show up. And it was a disaster in the US because no one had any idea about how to deal with that number of infections at the same time. They didn't have airborne infection isolation rooms. And so we scrambled to figure out how to turn arenas into temporary medical facilities, or how to convert an ordinary patient room into an AII. So yes, I think the healthcare community should be engaged right now in figuring out how to protect itself from any kind of event like that may happen in the future, maybe an H5N1 pandemic, which we expect every year, and it just hasn't happened yet. So that's important. And let's see, I've kind of lost the end of your question. The other types of facilities you talked about.
The other facility when we have a lot of general public traveling, like the public transport system, schools, and everything.
Yeah, transportation. Yeah, I testified to a congressional committee on transportation and infrastructure. I think it was in 2020. And I was impressed with how poor the air quality was, especially on buses. They were probably the worst because those fleets are often all sorts of ages and conditions. Airplanes, pretty good with the high air change rates and HEPA filtration, but yes, public transit also needs to be looked at, and I don't think we've done very much about it besides suggesting that maybe you should open the window.
Can I make a follow-up, sir? I just want you to be aware that in all the major facilities in Hong Kong in terms of air conditioning ventilation, the one who's running them have very strong background in mechanical, electrical, and equipment, so on and so forth. In general, their knowledge in airflow is close to zero. I'm afraid to say that because I wonder whether they can still remember the basics of fluid dynamics. But I think the government could do something by providing, or the academic institution like the Poly utilize cost disciplined training at the technician operation level to providing them the ability to understand the environment and conduct necessary certification tests to certify them as certified operators. That's my suggestion. Thank you.
Yeah, I strongly agree with that, and I do think that there is a workforce development issue that needs to be addressed. Even if we had the regulations we want tomorrow, do we have the people to do assessment and to do remediation? I think the answer to that is clearly no. And having been educated as a mechanical engineer, I can say that we learned very little about human factors in a mechanical engineering course. We learned a lot about thermodynamics and fluid mechanics and heat transfer, but the whole world became a control volume problem to solve energy and mass flow balances. What we didn't learn was how do the things that we do to maintain the indoor environment affect the performance of people. At best, we learned that there were standards that told us what we had to do, but we really were not enlightened. So I would like to see a lot more of that kind of education and any curriculum that is sending new workers into the building design field.
There are also a number of questions from the internet audience. The first question is, you talk a lot about the indoor air science, but very few of them are being converted into the real solutions of our buildings. So don't you think there's any disconnect there between the science and the reality?
Well, that's partly why I'm here giving this talk, is because I believe that there is a lot of truth to that. And, I think that we all need to be humble and to learn about how the whole process works. So frequently scientists will say, I've solved the problem, here's my answer, use it. And on the other hand, you have those who are owners and write standards, and they say, well, you don't understand how the real world works. That's not practical. And somehow we have to have a continuous dialogue. This isn't something where we can have a meeting and work everything out. We need to have engagement in the process. I would like to see research and technology development more informed by user needs. And I would like to see the scientific community being more educated and able to participate constructively in the regulatory process. It's really not good if your only way of trying to influence standards is to write op-eds for the New York Times or to go to meetings and complain about the people that write those standards. When I see you at the table, I will know you're serious about solving these problems.
Yeah, there's another related questions. There are also now a lot of new building materials being available on the market. The climate change also bring the new risk for the pollutions in the indoor spaces. Now, the experience we learned in the past in improving indoor air quality might not be suitable. So do you think they needed to be iterated and improved to solve the new challenges we have?
Are you saying because of new materials?
New materials, climate changes, right? Those are the new things that probably will have the impact on the indoor air quality. For example, you look at these seminar rooms, we use this still look like a wood, and they have
It looks like hardwood, yeah.
Yeah, sometimes they're not real wood, and then not real leather, right? They emit a very different type of pollutants.
Well, certainly we have to keep changing our standards based on the technology that's available, right? Those are the boundary conditions of what we're dealing with. So new materials need to be, I think they need to be vetted before we put them in buildings. I think the way product safety research often goes is we put something on the market, and then if we find out that there's something bad about it, then we fix it. That's happened with many chemicals that we've used in food and in materials. So yes, we need to pay attention to that. And as far as climate change is concerned, we're just getting more and more pressure to not use outdoor air as the primary means of controlling indoor air quality. So we always need some outdoor air because we will never know everything that's in the environment, and that provides us a baseline of security. But as I said before, I think the future is really figuring out how to make air cleaners work, which means resolving their performance characterization and byproduct harm potential, and also answering the question about what exactly is it that we need to control. There are lots of problems lurking. Air cleaners tend to be tested against a certain challenge, and it's just that under certain controlled conditions. So what happens when I put that into this room where there are dozens of things competing for, say, sorption sites on a sorbent? So we really need to dig more into the practical application problems, which I think are full of rich research opportunities. We can make things simple for ourselves by just looking at one contaminant at a time, but if that's not the real world, that's not the way we need to do it in the end. And the issue of byproduct production of air cleaners, we've been studying the performance of air cleaners. What do they do that's beneficial for decades? And it's only been in the last few years that there's really been close attention to, well, are they doing anything harmful at the same time, producing ozone or producing secondary organic aerosols or all of these other contaminants? And so we are going to have to rethink, is this a useful technology, even though it has some negative aspect? And some may say, no, we have to forbid that. But think about where most of the ozone comes into a building in an urban area. Ozone levels are higher outside than inside. So is more outdoor air the answer? Maybe not.
Any more questions from the audience before I ask additional ones? Yes, please. Okay. Okay, this one first, and then there, and then Professor name. All right, you go first.
Thank you. So just one more suggestion on the how science community could support on this. So we're working with various sectors, including the corporates. So we know that they would be adhering to certain reporting guidelines. So there's a Hong Kong EX guideline that doesn't include IAQ at this moment. But then, for example, GRI, the Global Report Initiative, that would be very influential. But right now, what we see is that there's still a gap between, for example, ASTRA or other professional institutions guideline with the GRI, and then also for the ILO, the International Labor Organization or standard. So among the occupation safety and health industry, they look upon on ILO or the International Labor Standard to look at what kind of employee health and well-being they should look into. So I think it would be very beneficial if the science community would continue to have that effort and then make sure that gap could be closed between multiple professional institutions or guidelines. Thank you.
Yeah, I agree. And just taking ASHRAE as an example, we have a memorandum of understanding and collaborate with organizations like BOMA and IFMA that are active in Hong Kong, and with the American Industrial Hygiene Association. I think those are really useful partnerships. We don't need to develop all that expertise ourselves. It already exists, and those collaborations will make our efforts even stronger.
Yeah, hello, Professor. Thank you for your presentation. And when people are talking about the indoor air quality, maybe they just refer to the operational stage. So my question is, what can we do during the design stage? Can we do something earlier? Yeah, at the beginning of the project.
Yeah, well, good air quality starts with keeping sources of contaminants out of your building that you can eliminate. And so there's a role for architects and interior designers at that point. And then, to the extent that we're relying on outdoor air to ensure that there is a reliable source of outdoor air. Many systems have a hard time controlling it under varying operational conditions. Making systems maintainable is important. Having enough sensors to know what a system is doing. I think this has been a persistent problem as well, is that you have to bring in instrumentation to figure out things like what is the outdoor airflow in this system, and then to design in resilience. I think going forward, we must consider resilient operation for buildings relative to whatever the main risks might be, which would be wildfire smoke and severe infectious disease outbreaks at least in the U.S. and in many parts of the world. So I think that the principles are pretty simple, and we can achieve a reasonable standard by making sure that we don't set the floor too low. Standards are always going to be the floor, the worst you can do, but we forget that if we just take the worst you can do and keep pushing that slowly upwards, towards where we want to be, that we can make a huge amount of progress.
Yeah, thank you.
Okay, thank you, Bill, for the inspirational speech. And I can't just help to recall that right in this room we had a very first discussion about that's at the outbreak of SARS in 2003. Alex was also here. My observation over the years that airborne, when we talk about airborne infection, seems our professionals, our government officials, including WHO and the CDC, tend to be fairly conservative when a new emerging disease arise. They before we know anything, they tend to say that it's not airborne transmitted. That occurred with SARS. That occurred with the COVID-19. In working with WHO in producing the ventilation guide for hospitals, we also communicate with quite a number of our colleagues from WHO. We had the feeling that I don't know why many of our colleagues tend to accept that a disease can be airborne transmitted. With COVID-19, you know that only after the open letter led by Lydia Morozka and Don Milton that the CDC and WHO changed their stances, and that was quite a news for all the medias. What is your insight on this phenomenon? And actually, sometimes I joke with my colleagues, the mistakes were all made over the years regarding with the SARS and the COVID-19 probably would happen again when other new emerging diseases occur. So anyway, that's my comment.
Yeah, well, that's a very difficult problem. Is detailed in that book, Airborne, this idea of are there airborne diseases? First, it was just debunking the miasma theory, which really was just made up. But after Chapin, it was viewed with relief that we could believe that the diseases weren't transmitted by the airborne route, because then everybody felt safer. And they actually said that back in those days. And so whenever there was evidence of airborne transmission, after that, there was a lot of pushback against it. Now, with WHO and CDC, I think that you have organizations that are staffed by people who are trained in the public health and infection prevention doctrines of their time, and they just weren't particularly willing, until a lot of public pressure was brought to bear, to concede that maybe they were wrong. And the thing that surprises me the most, though, is that they should have been the ones that were standing up for the precautionary principle here, and recognizing that there was enough concern about airborne transmission that we ought to do something about it. There were all sorts of arguments put forward. Oh, well, we need to save the N95 masks for healthcare workers. That was one of them, but that went away, and it still didn't change the response. I should say, though, that the first masks I got after COVID started were sent to me by a colleague at Tsinghua, who emailed me and said, "Would you like some masks? I understand you don't have many in the U.S." And I took them. And so it's a very complicated thing that involves professional silos and maybe a little bit of ego, that you don't want to be willing to change your opinion. But if you're not willing to change your opinion, you're not really a scientist, are you? I mean, that's what science is all about, is being persuaded by evidence. And that's what I think we need to do in the future, and whether we'll be able to do it remains to be seen.
Okay, maybe we can accommodate one more question. Okay, if not, I have a question. You just show the history that will repeat, right? And a lot of measures you impose early days for SARS, and then you impose again the similar thing for the later events. Now you see pandemic is, especially I will say airborne pandemic happens every few years. SARS, then the swine flu in 2009, and COVID in 2019, and I don't know, maybe in 2029 will be another one. So why it's so difficult to implement the measures you have imposed some 20 years ago?
I think the main reason is that we're very eager to move away from periods when things are bad and get back to normal. So that's one of the things, is that people don't want to feel like there's an urgent need to do anything anymore. And also there's always the distraction of current priorities that may be more pressing, cost of living or whatever it is. So I think in that environment, it's been hard to raise the level of concern to the point of doing something long-lasting. Many jurisdictions had pandemic plans, but they didn't practice them. Some didn't have them at all. I think it's the commitment to preparedness, knowing that it's going to happen again, even though it may not be tomorrow, that we have to somehow instill. We don't wait for an earthquake to agree that there's enough concern that we ought to be designing buildings to guard against them. We design for earthquakes. Not every building catches fire, but every building has fire protection. I think that there are many examples that we could come up with that illustrate how in other areas of life we take risk seriously enough to do something about it. And so that's I think the question for everyone is, how do we make that case that this risk is severe enough? And I think it's partly going away from it's got to be a pandemic for us to do something about it that's killing millions of people. Think about the burden of disease. So we're happy now that COVID has settled down to be an endemic infection, but as many people are dying from COVID in the US as we're dying from influenza in a typical year. And so now we've essentially got flu times 2. That could be 100,000 people a year, and it's millions of sick days and hundreds of thousands of hospitalizations. Think of the healthcare cost of that we're paying. And so somehow we have to make people see it so that we'll do something about it.
Okay, well then, thank you again. Bill, please join me to give Bill another round of applause. So to express our appreciation to your lecture, we prepare a small souvenir for you. This is just a souvenir with your name and the lecture title today here. So it's a specially made gift for you.
Thank you very much.
All right, thank you, everyone, especially those who from outside our Purdue. We appreciate your participation in this seminar. And now the seminar is adjourned. Thank you.